10 feet. Is that right, Miss Stewart?
It is.
And we have Bart, and I drew, I think, a beautiful version. Well, don't worry if you can't draw it quite as well as I can.
That is very nice.
So Bart is standing 6 feet from the wall, and the ladder is sliding down. And the rate at which the ladder is sliding down the wall, the top of the ladder, is it's sliding at a rate of 1 foot per second.
Okay.
So the first thing I'm going to do is I'm just going to label everything with a variable that in my diagram here. Let's call this x, this distance right here. And at this moment in time, x is 6. Let's call this y. I'm not sure what that is actually right now. Let's call that z. X, y, and z, is that working for you?
I'm liking it.
Well, I guess I could use the Pythagorean theorem to figure out what y is at this moment in time. And this
Sure.
is a nice triple here. 6 squared plus something squared equals 10 squared, or 100. And I think I can do this one off the top of my head.
I think you
actually.
can.
I think that's going to be an 8. What do you think?
I love those Pythagorean
4
triples.
plus 36 is 100, so that works. All right, so let's write some equation which relates these variables about the Pythagorean theorem. X squared plus y squared equals z squared. I want to figure out how this is changing. I want to figure out the rate of change, and of course a derivative is a rate of change, so I will take the derivative of this.
Why don't you throw a squared on that z?
Thank you very much.
You said it, but you didn't write
Well, you know, sometimes that happens.
it.
That's why I have you watching me there.
Well,
Miss Lewis.
good.
You cannot be trusted, obviously.
That's right.
So let's take the derivative of this guy, 2x. Now remember, we're using implicit differentiation. Everything is changing with respect to time, so I'm going to add the derivative of x, or the difference in x, over time. This means x is changing over time, plus the derivative of y. Y is also changing over time. Change in y, difference in y over time, equals to z dz dt. Am I off the side of the board there, Ms.
No,
Stewart?
you're great.
Okay.
So that's interesting. So you're taking the derivative of each variable with respect to time.
That's exactly what I'm doing.
Very
Exactly.
cool.
Everything is changing with respect to time. So this is really implicit differentiation, but instead of doing dy dx or dx dx, everything is changing with respect to time.
Fantastic.
That's the derivative. A derivative is a rate of change, or a slope. That should tell me how everything is changing here. So I'm just going to fill in the information that I have. X at this moment in time is 6. dx dt, that means how fast is x changing? Well, that's what I'm looking for. I want to know how fast the ladder is moving at the base when it hits Bart. I don't know what that is, and as a matter of fact, that's what I'm looking for, as I said. Plus 2, I know y at this moment in time. dy dt, that means how fast the ladder is sliding down the wall. That's how fast y is changing. And in the problem it says the top of the ladder is sliding down the wall at 1 foot per second. I'm going to make this -1. You know why, Ms. Stewart? Of course
Well,
you know why.
yeah, because y is getting smaller, and so your rate has to be negative.
That's going to be important. If the length of something is decreasing, you're going to have to call it negative, or your problems are going to come out all kooky. If this had been increasing in length, I would have called it positive, whatever. Equals 2z, I know is 10. dz dt, how fast the length of my ladder is changing. I don't think the length of my ladder is changing.
I don't think so either.
So I'm going to call that 0. Interesting. So now I just solve for dx dt. This, of course, is 0. So I have, let's call this 12 dx dt equals, what's this going to be? Well, this is 0. This is 16. It's -16, actually. So I'm going to move it to the other side. Positive 16. Is that maneuver all right?
Very nice.
So dx dt equals 16 over 12. Were you going to say something, Ms. Stewart?
I was just going to say you're just doing algebra at this point.
I'm just doing algebra at this point. I'm just solving for dx dt, which is how fast the ladder is moving, and I'm done. 4 goes into that 4 times, goes into that 3 times. So dx dt is, let me just squeeze it right here, dx dt equals 4/3. And what are the units of that?
That is an excellent question.
Feet per second. So 4/3 or 1 1/3 feet per second is how fast the bottom of the ladder is moving when it hits bar. And there
How
you have
cool
it.
is that?
That's very cool.
These problems, of course, are called related rates problems because I've got rates that are related to each other. Let's say I've got a puddle, isn't that a lovely looking puddle? And let's say there's water dripping into this puddle so that it is getting bigger and bigger and bigger. I think you would agree that the radius of the circle is getting bigger and the area of the circle is getting bigger, but not at the same rate. Those rates are related to each other, but they're not growing at the same rate. We'll play around with this in class and you'll be able to get a sense of that more intuitively. But let's just go through the nuts and bolts about how to do this. Let's say I've got my puddle and I'm interested at the moment in time when the radius is 10 inches. Let's say that the radius is growing at a rate of 3 inches per minute. Well, so that's the rate at which the radius is growing. I'm just going to call that dr dt, right? So let's say that's 3 inches per minute. And what I want to know is, how, at that instant, how fast is the area growing? In other words, what is dA dt at that point in time?
So now if the radius had been shrinking, if the puddle was evaporating, then dr dt, that just means change in radius over time, you would have made that negative.
Negative.
Radius decrease. Got it.
That's
All right. Thanks,
so
Ms.
my
Stewart.
radius is getting bigger, so my rate is positive. Had I like the evaporating idea, then the radius would be getting smaller, which means my rate would be negative. Good. All right. So always with these related rates problems, you want to come up with an equation that relates your variables. I've got area, I've got radius. Call me crazy, Mr. Haas, but I'm thinking.
That's looking like area of a circle. I'm thinking.
area
Yeah.
of a circle, which, as we all know, is pi r squared. There's an equation that relates my two variables. I want to see something about their rates. To find a rate, I take a derivative. And we're taking derivative with respect to time. Well, we'll see how far we can get. Our battery's dying, so we'll go quickly. All right, derivative of a dA dt, that's not bad. Derivative of pi r squared, that's just a variable. That's like 3r squared. I'm just going to bring the 2 down. 2 times pi times r. Chain rule times the derivative of r, dr dt. Let's just plug in everything I know. dA dt is what I'm looking for. 2 times pi. At this instant, my radius is 10, and the rate is 3. So there we go. 2 times pi times 10 times 3. That looks like 60 pi is my rate at which my area is changing. And my units would be square inches per minute. So at this moment, when the radius is 10 inches, my area is changing at a rate of 60 pi square inches per minute. I think we made it before the battery
That's
died.
fabulous. Yeah, we made it.
Excellent.
Mr. Blue Skies, tell us why you had to hide away for so long. Where did we go wrong? Hey there, Mr. Blue Skies, so blue.